welcome back. Today we will look at the rate equation of the first law of thermodynamics and then go on to the first law for a control volume. So far we have been writing the first law in generally this form. So we have a small amount of heat transfer being equal to a small change in internal energy and kinetic and potential energy. We also usually club all of these together as dE, and then we have work, or we also often write it in this form, dE is del Q minus del W, which we can then integrate as delta E is Q minus W, going from some point 1 to a 2. What we can do is divide this expression by del T. So then we get this kind of expression, and we can take the limit of del T tending to 0. So essentially divide by very small del T's. So then this is what we would call as dE by dt, which is the change in energy with respect to time. This in the limit of del T tending to 0 this is what we call as the rate of heat transfer, which we usually denote as Q dot, and this is what we call as the rate of doing work, which is what we call as power or W dot. So the rate equation is essentially this. We have been writing this for a control mass, so we just have the Cm to emphasize that this is for control mass. So the rate equation is essentially this, or you can write it with Q on this side and dE by dt on the other side. So we get an expression of this form. We have been actually using this expression even though we never formally wrote it down. We have been using it anyway. For example, if we have a system of this kind where we have a battery, a motor and a light bulb, we have been using these equations. So if I have, for example, each of these I take individually, then what we can see is if we take the bulb, there is electrical work being done on this bulb because there is power from a battery, a DC battery in this case, which is powering this. So if I take across this boundary, I have voltage coming in, current coming in at a higher voltage and going out at a low voltage. So there is work being done, and we have been calculating this power as voltage into current, and we have also been finding out the work as V into I into T. So we have been using this expression in some form. Now this bulb itself, we would usually assume it to be at steady state. So if I have a bulb on, I switched it on, let's say 5 minutes back. So it has reached some temperature, it's giving out light. If I look at it after like say 5 minutes, the temperature of the bulb does not change. Light which is coming out is essentially the same, is what I would expect if I had a constant source. So for this bulb, I would generally assume that it is in steady state, which means that nothing is changing with time. So if I was to write the first law for this bulb, so I would have the first law now as dE by dt is Q dot minus W dot. If the temperature, this bulb is not moving anywhere, so its potential and kinetic energy are the same. If its temperature is also the same, then the internal energy is also the same. So essentially this E, which is for us a sum of the potential energy and kinetic energy and internal energy, none of them is changing with time if the bulb is already on and it's remaining in steady state. So then this term goes to 0, and then what I see is that any heat emitted by this bulb should be equal to the work done on this bulb by this. So I can find out the value of Q dot, which should be equal to this V into I into T. So this bulb is of course giving out electromagnetic radiation in the form of light or heat. So if the radiation is in visible wavelengths, we call it as light. If it is in the infrared, we call it as heat. So as far as the wavelengths are concerned, but in general all of it is in the form of, from a thermodynamics perspective, all of it is in the form of heat of varying wavelengths. Some of it is in wavelengths we can see, some of it is in wavelengths we cannot see, but it is radiated out as heat. So we are doing work on this device, it is converting it into heat and radiating it out. Of course, there could also be some convection and convection from the surface because the bulb itself is hotter than the atmosphere. So, that is essentially what we see. If we want to now analyze, for example, the fan in this case, we could do a similar analysis, or even for the battery. So, if you look at the battery now, the fan would be very similar to the bulb. So, you have work which is being done, but in the case of the fan, it is doing work outside because you have rotation of a shaft, and we said that the rotation of a shaft, you can think of it as being equivalent to lifting of a weight. So, the fan would do work. So, that is all right. But now if you look at the battery itself, we have this battery over here. So, let us take the control volume as this drawn just around the battery. So, we have electrical work which is going out because there is current being pushed out of this battery. So, we have W dot. If there is any heat transfer, which usually happens, for example, you have a mobile phone, you keep it on for a while, let us say you are doing something demanding on it, it becomes a little warm, the battery as it discharges releases some heat. So, then that would also be Q dot. And if you were to write the first law for this, what we see is that the rate form of the first law essentially tells you dE by dt is Q dot minus W dot. So, this is what we have. So, the battery is not moving. So, generally we say E is potential is internal energy plus potential energy plus kinetic energy, that is what we have been always saying. So, the battery itself is not moving. So, this is 0, sorry. So, it is this also is 0 because it is at the same level. So, the level is not being changed. So, this is 0. It is also not moving. So, there is no kinetic energy involved and any changes also are 0. So, I can also write this as du by dt is Q dot minus W dot, which is the first law for this battery system. So, what I see is as I use this battery for longer and longer time, it is doing work, and it is also giving out heat. So, giving out heat is, we had the conventions earlier, we said that if heat is coming into the system, it is positive, work going out of the system is positive. There is no work coming into the system here, and there is no heat coming into the system, heat is going out of the system, which for us is negative. And what we see is that the internal energy of this battery will keep dropping because it is giving out heat and it is giving out work. So, the internal energy will keep dropping. At some point of time it becomes so low that it stops doing work. So, this is an unsteady process. So, initially what we see is that the internal energy is some value, and after a while if we find out the internal energy, we will find that it is a lower value and lower and so on, because it is giving out energy by running this fan as well as running the light. So, that is essentially what we see. So, if I wanted to find out how much is the change, I can of course, if Q dot and W dot are constant over a period of time, then I can find out delta U as Q dot minus W dot into delta T, if this was constant over a small period of time. If these are changing, then of course I have to integrate them. So, that is one way in which I can find out the change. So, this is for a control mass where the mass itself is fixed even though the energy is changing with respect to time. The more common kind of a scenario is where we have the mass as well as energy changing with time, and we usually deal with these things as in the form of control volumes. So, we are going to do control volume analysis. So, let us say you have some arbitrarily shaped volume, it can be either like this or any other shape. We can draw a control surface which sort of demarcates our volume, and let us say you have some mass which is coming in, the rate at which it is coming in is m dot in, you have mass going out, the rate at which it is going out is some m dot out. So, we can write a mass balance for this device. So, examples of these would be, you have a bucket, you open a tap and you are trying to fill it. So, there is some rate at which mass is coming in. So, let us say I want to find out how long it will take for the bucket to fill. So, that is one kind of a system. So, I have a control volume there, the bucket is the control volume. I have mass entering the control volume from say a tap, which is m dot in. Let us say there is a leak in the bucket, that is m dot out. So, I have a leaky bucket, there is a small hole at the bottom, I am trying to fill it in. Is it possible to fill it completely at all? So, common sense says that if I have mass coming in at a high rate compared to what is going out, I can fill. So, that would be the change in mass of the control volume. So, similarly, I can have a control volume with multiple inlets. So, I have like say 2 taps, I have a hot water and a cold water tap, I open both and I am trying to fill something. Let us say there are 2 holes in it, I have 3 taps, let us say I have 2 holes in the bucket and I am trying to fill. So, all of these would be cases where we have mass transfer. We can also have heat transfer, but we are not looking at that for the moment, we are only looking at the mass balance. So, we will go on to the first law for control volume, but before that, in the context of that, we need to write down the expressions for the conservation of mass, and which is what we are going to do. So, we have this control volume, the change in mass, we usually call it as small m, even though it is written as capital M here. The change in mass with respect to time for the control volume should be whatever is coming in minus whatever is going out. So, change in mass is always final minus initial. So, whatever, if you have mass coming in, then final mass should be higher, which is what this says. So, if I have only one inlet and one outlet, so I would have dm by dt is m dot in minus m dot out or exit. So, for short form of writing, we usually write as inlet minus exit, or you can also write in minus out, it does not matter, all of them is any convention which you are comfortable with should be all right. So, we say the change in mass with respect to time should be the rate at which stuff is coming in minus the rate at which stuff is going out. I already have a dot here. Yeah. So, we can also look at this with respect to other things. For example, I have a wallet, I put 10 rupees in every day, I take 5 rupees out every day, what will be the money I have in my purse tomorrow? So, it will be whatever I have today plus I put in 10 rupees today. So, it went up by 10 minus I removed 5 rupees today minus 5. So, whatever I have today plus 10 minus 5 will be what is there. So, for example, if I wanted to know how much is there after some time, I take m dot in minus m dot out multiply by dt, and that tells me what is the change from, let us say, tomorrow to today or 1 hour later to now. So, that is essentially what this expression says. So, dm by dt is final mass minus initial mass divided by the time at which I am finding out. So, what I am of course assuming is that is m dot I and m dot e are, if I want to integrate it, they either have to be constants or I need to know how they vary. So, for example, let us say I have a purse, I am trying, or I have a piggy bank, I am putting money into it. So, let us say today I put in 10 rupees, tomorrow I put in 20 rupees, and at the end of 3 days I want to know how much money is there. Then I need to know how this m dot I over there, the money going in, varies as a function of time. So, I need to either know the average rate at which money is being put in, or I need to know as a function. So, today it is 10 rupees, tomorrow it is 20 rupees, the day after it is 15 rupees. I need to know how it varies as a function of time. How much is being put in, I need to know how it varies. So, these I can only integrate if I know that they are constants or if I know how they vary with time. If I have more than one inlet, so if I have another inlet, so let us say this is m1 dot in, this is m2 dot in, and so on, and if I have more than one outlet, then of course what I need to do is sum up all of them. So, then my dm by dt would be whatever is coming in. So, that is m dot 1 in plus m dot 2 in minus m dot 1 out minus m dot 2 out, which is essentially what we write as sigma. So, the general form in which we write this is dm by dt is sigma m dot in minus sigma m dot out, which says that I should sum over all the inlets to add mass here. I should sum out whatever is going through all the outlets to remove whatever mass is going out, which is sort of written in this form. So, we have, for example, this filling problem here. So, if I have a tank like this, I have m dot in, I have m dot out. I initially had some mass in this. If I want to know how the mass is varying with respect to time, what I would do essentially is find out what is going in and find out what is going out and take the rates. So, if I had nothing coming in and nothing going out, so if both these were closed, then dm by dt is 0, which says that m dot final is equal to m dot initial and there is no change in the mass. If I have only m dot in and I do not have m dot out, then what I will see is this will be 0, and if this is coming in at a constant rate, I can tell you how long it will take for this tank to fill. Or for example, if this is closed and this is open, and of course I have small vent here so that air can come in, but air does not have much of a mass compared to the liquid. So, what I can see is that this will then empty, and I can calculate if the rate at which it is going out is the same, I can calculate how long it will take to empty this. But we know that the rate at which flow goes out is unlikely to be the same, because flow goes out depending, the velocity which I get here depends on how high a column I have here. So, I know that this will change, but if I have a way of knowing how it will change, I can still calculate what will be the mass flow rate which is going outside. We will possibly do a problem which shows that kind of a behavior a little later on. So, now that we have the conservation of mass, we can look at conservation of energy in a similar fashion. So, in all of these, what we are saying is the change in mass with respect to time of the control volume is essentially what is coming in minus what is going out. So, we are going to use the same principle for energy. So, we are going to say the change in energy of the control volume is whatever with respect to time is whatever is coming in minus whatever is going out. So, we have over here systems which have varying mass. So, for example, this shows a bathtub where we are trying to fill it with water. We know that if we have the bottom closed, then the liquid of water, sorry, the level of water will keep increasing. So, we would use the formula we just discussed. Similarly, blowing a balloon, initially there is no mass inside the balloon. As you blow it, the volume is changing, but the mass is also changing. So, we could use a control volume analysis accounting for the fact that the volume is also changing for this case. Here we could use a control volume analysis assuming that the volume is fixed. If we take the entire bathtub as the volume, this shows a compressor. Let's say we are switching on the compressor, and there is a tank here. The compressor runs and fills high pressure air into this tank, which we can then use for example, for running a power tool, or if you have a cycle and you want to fill air in its tires, you may use this, or filling in a vehicle of some other kind. So, in this case also we could assume that this red tank here is a control volume. The volume is fixed, but as we compress and fill in air, the mass of this tank becomes higher. As we discharge it to fill somewhere else, then the mass becomes lower. So, we would use the previous expressions. We will also look at some of the other expressions which we usually use. So, the volumetric flow rate of substance going in or out of these tanks or in and out of this is given by the velocity. This bold italicized font denotes velocity into the area. So, we know, so volumetric flow rate has units of, for example, meter cube per second, area has units of meter square, velocity has units of meter per second. So, meter per second into meter square will give you meter cube per second. So, this would be something like that. Now, the thing is that if I have a pipe and I have flow coming out of this pipe, the velocity profile at the end of the pipe does not have to be uniform. So, what we may like to assume is that the velocity near the walls as well as the center is uniform, but we know that there is viscosity for real liquids, and the pipe itself is not moving. So, what we would generally see is that the profile of velocity would be something like this. It is not the same everywhere with respect to the diameter of the pipe. So, what we would generally know is the local velocity. For example, here the velocity is something, here the velocity is higher, something else. So, what we may usually have to do is integrate the local velocity to get the volumetric flow rate. So, instead of having like one velocity all through multiplied by area, what we would usually need to consider is that in this small area, for example, from here to here, the velocity is something. In this small area at the center, the velocity is something else, and so we may have to integrate the local velocity times area to get the volumetric flow rate. If the flow is incompressible, if the fluid is also incompressible, so what we can do is find out the mass flow rate by multiplying the density times the volumetric flow rate which we have got. The density is spun by specific volume. So, we can write this as velocity times area by specific volume, or we can also write it as rho times area times the velocity. Okay. So, when I am writing the velocity by hand, I can't write in font. So, what I am going to do is put a bar on top to sort of tell you that this is the velocity rather than the volume, because I also use capital V for volume. So, this is specific volume. So, this is also A into this divided by V. So, this is essentially the small v over here. So, we can get the mass flow rate in this form. If the density is also changing, then what we need to do is we need to put this density also inside and integrate. So, for the control mass, we saw that the rate equation is of this form. We said it is dE by dt is equal to q dot minus w dot. Now, the question is what happens in a control volume? This is all right for a control mass because the mass is fixed. There is energy being transferred across the boundary, but the mass itself does not change. But there is a little more complication in the case of a control volume, because not only can I have energy being transferred across the boundary or work done across the boundary, I can also have mass coming in. And the mass coming in can come with some kinetic energy, it can come with some potential energy, it can also come with a different temperature. So, it can come in with a different internal energy. It can also come in with different species. For example, I can have mass coming in as fuel, going out as exhaust. So, there is mass balance, but I can have the energy of the mass coming in being very different from the energy which is going out. So, we have that kind of a control volume here. So, our dotted lines indicate the control volume. So, we have some energy of the control volume which is changing as a function of time. So, the difference is the change is what we call as dE by dt, which is what we were also seeing earlier. Only thing is earlier we were looking for a control mass, now we are looking for a control volume. So, what we said for the mass conservation, we said essentially if I have only one inlet and one outlet, we said it would be something of this form. Whatever is coming in, the rate at which things are coming in minus rate at which mass is going out. Over here, we would have a combination of this as well as these terms. So, for example, I have heat which is coming in, the net heat which is coming in, I can have some going out. So, the net which is coming in which would be like this. I have net work done which would be like this, but then I also have mass which is being forced in. So, the question is how do I get mass to come into the control volume? So, I have for example a pipe which is connected to some control volume. How do I push this mass into the control volume? So, if I just had for example liquid in a pipe, this liquid is not going to flow, it is just going to sit there. I wanted to go inside this. So, for example, this is this pipe. So, I have a long pipe, or let us say I draw a slightly different control volume where it is easier to visualize. So, let us say I have a control volume of this kind. So, I have liquid here. this liquid does not want to go into my control volume, but I am pushing it and making sure it goes in and goes out here. So, in order to push this liquid in, so my control volume, let us say, is this. In order to push this in, I need to do work. So, I need to push this liquid in, which means I am doing work on the liquid. So, that is something which I need to take into account. Similarly, when this fluid is going out, this control volume is doing work on the fluid which is going out and pushing it out. So, the control volume is doing work on whatever is going out. So, we need to do work here on this control volume, or the surroundings need to do work on the control volume, and here when it is going out, the control volume is doing work on its surroundings by pushing out fluid. So, these are two additional terms which we need to take into account when dealing with a control volume. So, we have for the control mass the earlier expression. At the control surface, the fluid which is coming in is bringing with it energy, because the fluid has some temperature, it has some velocity, it is coming in at some height. For example, here it is coming in at this height, it is going out at some other height. So, the fluid here has some energy E, the fluid here has some energy also E, which corresponds to the exit. This is E corresponding to the inlet. So, those need to be taken into account. So, the fluid has internal energy, it has some kinetic energy, it has some potential energy when it is coming in. Similarly, when it is going out, it has some internal energy and kinetic and potential energy. Now, for pushing in the liquid into this control volume, the work which we do is what we call as the flow work. The work which you have to do in order to make sure that the liquid goes into the control volume is what we call as the flow work. So, the rate of flow work would be essentially the power. The power would be essentially the velocity into the force. So, the force is essentially pressure times area. The velocity is something which we are calling as c over here, that is the changing velocity. So, CTA, if I integrate, would give me the average velocity, which is capital V. So, I can write it in this form. So, what I can do also is that if I take velocity times area, it gives me flow rate, and then I have pressure here. So, I can just take these two terms together and this term separately and write it as pressure times the flow rate, or I can also write this as pressure times the specific volume times the mass flow rate. Okay. So, this is rho AV, this is flow rate. Yeah, so I can write this as pressure times the specific volume times the mass flow rate, where the specific volume is capital V by M. So, that is something which I can write. So, the flow work at the inlet is whatever is the pressure at the inlet times specific volume at the inlet times mass flow rate at the inlet. Flow work at the outlet is pressure at the outlet times V at the outlet times mass flow rate at the outlet. So, what we see is at the inlet, for example, if I have this let us say I have some m dot I coming in at the inlet. At the inlet, whatever is coming in has an energy of E, plus I am doing some flow work to push it in, which is PV on a specific basis. So, it is PV into m dot is the total, on a specific basis it is PV. So, E plus PV is essentially what is being brought in into this control volume. So, when I want to push some liquid into this control volume, that I have to do this work of PV, which is called as flow work, plus this liquid which is coming in brings some amount of energy E. So, this E I can expand as internal energy plus kinetic energy, which is half V square, plus potential energy, which is Gz, and I have this PV which I am writing here. So, this E is essentially U plus kinetic energy plus potential energy, which is U plus half velocity square plus G times Z, plus I have this PV term here, which remains as PV. And what I can now do is I can rearrange this a bit. I can take U plus PV together, which is what I have done here, and then I have half V square plus GZ. This U plus PV, we saw that that is what we call as enthalpy. That was our definition of enthalpy. U plus PV was the definition of enthalpy. So, these two terms together I can write as enthalpy, then I have the kinetic energy term, and then I have the potential energy term. So, what we see is at the inlet I have some flow rate m dot, which is bringing along with it energy of this magnitude. It is bringing in some enthalpy because it has some internal energy and it is being pushed in. It is bringing kinetic energy because there is some velocity with which it is coming in. It is bringing some potential energy because it is coming in at some height. So, this is what it brings in when it comes. So, similarly at the exit I will have similar terms. So, now what I can write is dE by dt for the control volume is whatever is the heat which is being transferred to the control volume minus whatever is the work being done by the control volume in some form, maybe as shaft work or as electrical work or something like that, plus the mass flow rate which is coming in into the energy which is being brought in by the mass flow rate minus the mass flow rate which is going out into the energy which is being taken out by the mass flow rate plus any flow work which is coming in and as well as going out. But this energy and flow work we already could sum up in this fashion. So, what we can write it instead is we can write this dE by dt for the control volume as heat transferred minus the work done plus m dot I into this EI plus this PV, which is essentially the enthalpy plus the kinetic energy, specific kinetic energy, which we can write as V square by 2 or C square by 2 or whatever you want to write it as, plus GZI at the inlet. This is what goes in the bracket here, minus m dot E into enthalpy at the exit plus velocity at the exit, which gives us kinetic energy, plus whatever is the potential energy going out at the exit. So, this is essentially the kind of expression we get for the first law for a flow process. We have considered one inlet here and one outlet for this over here, but we said that our arbitrary control volume can have any number of inlets and outlets. So, if we have more than one inlet, what we do is we do use a sigma over the inlets and sigma over the outlets. So, inside this would again be a similar kind of term, enthalpy plus kinetic energy plus potential energy, and here we will have a similar kind of term, kinetic energy at the exit, enthalpy at the exit and potential energy at the exit. If we have multiple outlets and multiple inlets, at each exit whatever is the corresponding value, we need to multiply that by the corresponding mass flow rate at that exit and at that inlet. So, this would be the general form of the first law for a control volume. So, what I am going to do maybe is at this point take a break and then go on to the steady state steady flow energy equation, or essentially various simplifications of this first law.